So in a previous lesson, we looked at how light travels in a straight line, and the fact that light travels at what we referred to as a constant speed of 3 times 10 to the 8 meters per second, and we talked about how that speed was determined, which isn't really all that important. The important part was light travels at a constant speed. It's really, really fast. So that's fine, except that sometimes we observe some weird things happening. For example, when light changes into a new medium. Now, medium is anything that is used to kind of spread information or energy. So the medium can be air for like a sound wave or a light wave. It can be water as well. That's where the word media comes from. It's just a way of kind of spreading information. So when light enters a new medium, or for example from water to air, air to water, now we see that it bends. There's a picture just below that of a pencil taken from above, and it looks like the pencil bends. Now we know the pencil is very likely to be straight. It comes down here, it reaches that point, and then it bends a little bit. So you pull the pencil out and you find that it's not bent at all, which is a neat little trick when you're trying to fool a 2 or 3 year old. But we're a little older and smarter, and we know that there's more going on than that. We see the same type of thing. We see the same type of thing happening for somebody when they're like spearfishing. And I doubt very many of us have ever actually been spearfishing, but the whole idea of the spearfishing is that you actually don't aim directly at the fish. So let's say here's where your fish is. And I'm just going to calibrate the board for a second. Okay, so there's my fish, and I'm standing on the shore over here with my giant spear, and I'm going to try to spear that fish. And if I aim right at it, as we're going to see later, I'm not going to be able to hit it. So we're going to come back to this situation so that we can figure out where I should be aiming. If I can't aim right at the fish to get it, should I be aiming below it, to the side, above it? So we'll come back to that one in a little bit. So this bending of light we call refraction, as the title of the lesson would suggest. And there's a very specific reason that refraction, I should say, happens, and it's the fact that the light changes speed as it enters the new medium. So we talked about how light was constant, but that was for a vacuum. So where there's no material and it's just empty space. The easiest way for me to explain this is to consider if you're driving a car. So you get in your nice Formula One style race car, because we all have one of those, and we start driving down the road, but you get a little distracted because you're texting, which is a bad idea to do in any kind of car, let alone a $1 million vehicle. And so you're driving along the road and at a high speed. Now your tires are capable of going the same pretty fast speed on the road. And so here you are, you're moving along. I'm just going to put kind of a little starting point over here. And you're moving along at straight speed. And then you, unfortunately, go off the road because you're not paying attention. And so at that point, that front tire, and you can kind of draw this straight line of how you're going. Let's use an actual straight line from here all the way over to there. Okay, just like that, we'll say. So that's the direction that we were heading. And what's going to happen at this point is that right tire, the right front tire for that race car, is now no longer able to travel as fast because it's on the gravel, so it's going to slow down. But the problem is that the left tire, the driver's side tire, is still capable of traveling fast and will still travel fast. So how is it possible for the right tire to slow down, but the left tire to keep going fast? Well, the only way that that can actually happen is if it bends. So it's going to bend a little bit, and so once it bends, now it's going to go at a different angle, because that left tire can't travel as far as the right tire does in the same amount of time. So as it goes down like this, we can draw another little arrow there, another little line, say like that, to show the direction that this car is up here. So the direction this car is now moving like that. So, I'll just slide that back over to where we started. We see that the path of the car bends because of the speed of the car in one medium compared to another. And that's kind of what light does. It's a good analogy. It's not the exact same reasoning. Light doesn't bend because one side of it hits a material before the other. Well, it kind of does, but you're not going to be responsible for knowing why it happens, but just which direction. So if you're ever concerned about which direction the light is going to bend, then think of this race car, or your car analogy, when one tire enters the gravel instead of the road. Now, the interesting thing here is that in our situation, the car, or a light ray, if you will, is traveling in the direction I just drew that arrow, and in here it goes in that direction. If the car were to turn around, let's turn this guy around, then the exact opposite would happen, right? So it would be traveling up here, and now that right tire hits the road first, it starts traveling faster. The only way that right tire can travel faster than the left tire is if it turns in that direction, and then the car goes off like this. So it doesn't really matter which way the car is going. It's gonna bend. It's gonna follow the same kind of path. It goes that way, and then it goes this way. So just like when we're talking about reflection, we can draw this artificial line that is 90 degrees to the surface and measure all of our angles from there. We're going to talk about that a little bit more detail in a future lesson. But we can refer to this in our first circumstance when the car was coming this way. This is wave incoming, and an incoming ray we call an incident ray. So this here would be our angle of incidence, and then this would be our angle of refraction, which we're going to use a capital R. So the main thing I want to point out to you, when you're going from a high speed to a low speed, notice that the angle gets smaller. So this angle is fairly large, this one is smaller. So the angle, when you're slowing down, the angle gets small. When you went the other way, and you're coming up this way, and you're speeding up, the angle gets larger. So when you're measuring from the normal, the angle gets larger when you're speeding up and smaller when you're slowing down. So what we really want to focus on at this point is a little bit about the speed of the light in each material. So we have a ratio. If we look at the ratio of the speed of light in a vacuum, now speed of light in a vacuum, that's what we called C, to the speed of light in the material, and depending on which material you'll have, that speed of light will change. So we're just going to call that V. Think of V like for velocity. So that's a common symbol to use for speed, because velocity and speed are related. So this ratio of C to V is what we call the index of refraction. And we use a lowercase n to denote the symbol. So we could change this sentence, we could translate it from an English sentence into another language, that is the language of math. So the index of refraction, n, is equals the ratio. Ratio means it's a fraction, or think of dividing by. So the ratio or refraction of the speed of light in a vacuum to, so divided by, per the speed of light in the material. So n equals c over v. And c and v are both usually in meters per second, which means that the unit that we have is meters per second divided by meters per second. And so everything's canceled, and so we get no unit at all. This is one of those rare occasions where we have a variable that does not have a unit. That's because the units cancel, because it's just a ratio. Now, notice something about this particular number is that the ratio must always, there's a certain mathematical property. We know that c, this is the fastest light can get. So any speed that the light travels in a material different than a vacuum will be a little bit lower, or possibly a lot lower. So c is always going to be the larger number. So if you have a fraction where the numerator is greater than the denominator, when you divide c by v, you're always going to have a fraction or a ratio that is greater than 1. So if you're ever doing a calculation and you get an index of refraction that is less than 1, then there's a problem somewhere. Either you've made a math mistake, or there's something wrong with the question and the givens, or maybe it's just an impossible situation. That's one of those things that happens in science, is that you plug numbers into an equation and you get something that doesn't make sense, and it doesn't make sense because it was a physically impossible situation. Like if I said I threw a ball up at 1 meter per second and I asked you how long it would take to get a kilometer high, well, it never gets there. So if you plugged all the math in, you would get an answer that doesn't make sense. So if you end up with an n that's less than 1, then that just doesn't make sense. So you want to recheck your math, make sure that you have all the variables in the right place, and you've done any conversions that you need to, converting everything into meters per second. So I did say that I wanted to go back to the top here and take a look at our spearfishing incident and try to figure out where I should aim. So we know that when the light is coming from the fish, it's going from a low speed to a high speed. So it's going to bend away from the material, from the medium. So this is what's happening. Let's get away from the normal, I should say. So light's coming in here. That light ray looks like it's going to miss my eye. It looks like it's going to keep kind of going out in this direction, like that. But that doesn't actually happen. So what happens is that it bends away from the normal, and it makes it to my eye. Now my brain, thinking that I'm smart, says, aha, but I know light travels in a straight line. So if I just put this back right here, means that, oh look, there's your fish. So I see the fish in that spot, but it's not in that spot. It's actually a little bit below. So when I take my spear, I should, instead of aiming my spear directly in this direction, which is where I see the fish, I should aim my spear in that direction in order to get the fish. If we look at the situation with the pencil looks like it bends from our perspective here. If we're looking at it from like this, let's say my eye is like right over here, the pencil looks like it bends again because of the light. So the actual pencil, we know, is coming straight down like this. But the light coming from there is actually heading out that way, and then it bends when it reaches the top. So light's heading out there, it bends when it reaches the surface of the air, and it makes it to my eye. Maybe not quite so significant. Let's try that again. So the light is coming from the end of the pencil, which is actually like right here. So let's say this green, that's my pencil. So the light is coming out that way, and then it hits the top of the water and it bends. And so when we see it bend, we can follow that line. We get that my brain thinks that the pencil is located right over here because it thinks that light travels in a straight line when the pencil is actually located over there. And that's why it makes it look like the pencil is bent. So on the next page here, we have some values of n You don't have to memorize any one of these. Actually, that's not true. I would say there's probably one here that you should memorize, and that's air. In the same way that we might want you to know the density of water is 1 gram per centimeter cubed, we would probably want you to know that N for air, well, it's actually like 1.0003. So for all intents and purposes, we're just going to call it 1. Okay? So the index of refraction of air is 1, meaning that light travels at the same speed in air as it does in a vacuum. We're very, 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 very close to it. We don't look at this many significant digits in any other number, so why should we here? We'll just round it off to 1. For water, it's about 1.33. It does change. These things do change a little bit depending on temperature and pressure and things like that. But for all purposes that we're going to be looking at, water is about 1.3. Glass depends on what kind of glass. And it's going to generally range anywhere between about 1.45 and 1.65, depending on the type of glass and how it's made and whatnot. Ethanol is about 1.36, so really, really close to water. Ethanol is also known as ethyl alcohol. A ruby, about 1.54. And I've left the most interesting one for the last, and that's diamond, which is about 2.42. So you can see that it's really high here. And when an index of refraction is high, it means the light slows down a lot. And this is one of the things that makes diamond special and why it sparkles a lot, and we might see that in a future video. So let's look at a diamond. What is the speed of light in a diamond? So just like we did before, write down your givens. What do we know? We know that C is equal to 3.00 times 10 to the 8 meters per second. You won't be told that in the question itself. You'll have that along with the formulas, or you'd have to look it up. We know that index of refraction of diamond is 2.42, and we want to figure out what V is. So we have N equals C over V. We want V by itself, right? And we don't want it on the bottom of an equation. We want it on the top. So let's multiply both sides by V. So we get N times V equals, those are going to cancel, so N times V equals C. And if we divide out by N on both sides, we get V equals C over N. So we take 3 times 10 to the 8 divided by 2.42. Think of that as 3 divided by 2.42. Plug that in your calculator. Don't need any fancy calculator to do that. You get about 1.24. And you're still left with that times 10 to the 8. And it's in meters per second. So the speed of light in a diamond is 1.24 times 10 to the 8 meters per second. So diamonds have a really, really high index of refraction. There aren't very many, if any, natural substances that have a speed of light that is any lower than that. But that's still a huge, huge speed. It's still 124 million meters every second, or 124,000 kilometers each second. So even in a diamond, the speed of light is very, very fast. So take a look in your textbook. There's a bunch of pretty good practice questions and some alternative explanations. There's a few more lessons that deal with this whole bending of light that are included in that section 11.2. And so I'm just going to ask you to stick to the ones that are that deal with this lesson, and you will presumably do the next video on Snell's law and a bit more quantitative stuff about how much the light bends coming up soon.